I'm Wendy. As announced earlier, today's topic, partial hypothesis test, is the last topic of my intermediate statistics lecture. Okay, this topic is sometimes necessary for empirical studies. Let's see what is partial hypothesis test. The basic hypothesis testing dealt with in the a multiple linear regression model y equal to beta 0 plus beta 1 x1 plus dot 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 plus beta p xp plus epsilon are usually beta 0, beta j equal to 0 or not, okay? Null hypothesis like this, j equal to 1 to p. That is every explanatory variable necessary in the model or not. And h naught, beta 1, beta 2, beta p equal to 0. All the explanatory variables are useless, saying this null hypothesis. So it rarely happen, this kind of happen to not to reject this hypothesis. This null hypothesis is what? Almost always reject this null hypothesis. However, in some cases, it may be necessary to test the hypothesis of the form like beta j equal to beta k, any two specific explanatory variables equal to 0, or h naught beta 1 plus beta 2 equal beta 1 plus beta 2 equal to some value 1. Okay, let let us suppose the explanatory variable x1 and x2 are proportion, and theoretically the sum of what parameters beta 1 beta 2 equal to 1, or beta 1 plus beta 2 equal to 0.3. That is possible also. Okay, we call this kind of hypothesis testing is partial hypothesis test. These tests are conducted based on a specific background purpose, whether empirical or theoretical. Okay, to illustrate this, we need to know sequential sum of squares. Sequential sum of squares for the case with two explanatory variables. This is for a simple example. For a simple example, in the model y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon, only two explanatory variables. Okay, let's denote regression sum of squares, SSR. You remember regression sum of squares, SSR. Okay, SSR is yi hat minus y bar squared, sum of all this part. This part is what? In a simple case, slope. When we got a data and we got a line here, y hat equal to beta 0 hat plus beta 1 hat x, okay? Then there will be y bar here. Then some point, some value here. This one is y I hat. Where is xi here? Xi here. Then you get yi hat on the line. Then this part is yi hat minus y bar. What is that? This is a slope. Slope means slope may explain what? Your data. This line represents your data by line, linear line. Then the slope is important. Yi hat minus y bar. This one. So squared it, sum all the cases, we call SSR. So just simply reviewed previous thing, we denote it by x1, x2, x1, x2. This is explained by only two explanatory variables, x1, x2, right? When only one x1 is included in the model and x2 next added, the increase in the regression sum of squares is expressed as this way: x1 given, x2 SSR, okay, which represent additional amount of variance explained uh, variation explained by x2 beyond x1. This is variation, explained variation. Okay, then x1, sorry, SSR x1 x2 is x1 in the model, we get SSR, and next SSR x1 given x2. This is what increase in the regression sum of squares SSR when x1 included in the model, and next x2 is added, this amount. It is reasonable, right? You understand that? Equivalently, same thing. The order can be changed. X2 is first choice in the model, and after then, X1 is added. Okay? So this also holds. It means the order of explanatory variables is not important. Of course, SSR x1 x2 is not equal to SSR x1 plus SSR x2 because there is correlation between x1 and x2. Say, actually, regression analysis is for x1, x2, xp. Okay, then we say these what explanatory variables are orthogonal. Orthogonal is a complicated terminology, so I don't like to introduce orthogonal here. But anyway, you can imagine there is a correlation between x1 and x2. Okay, it is what we understand that kind of thing. So SSR x1 x2 is not equal to SSR x1 plus SSR x2. This one is right. Usually, this inequality holds. Anyway, next. In the general case, in the case of p explanatory variables, SSR x1 up to xp, okay, equal to SSR x1 plus SSR x1 given x2. Increase of SSR when adding x2 after x1. SSR xp given x1, x2, dot, 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 xp minus 1. Okay? This is a general expression of sequential sum of squares. These are called sequential sum of squares. All right. Using this relationship of sequential sum of squares, we can obtain sum of squares of a subset of explanatory variables. So for example, suppose there are 4 explanatory variables x1, x2, x3, x4. The partial sum of squares for x2 and x4, that is the increase in regression sum of squares, SSR, okay, when adding x2 and x4 to a model that already contains x1 and x3 in the model. Understand that? Is SSR x2 x4 given x1 and x3. We can denote that kind of thing is increase in the regression SSR when adding x2, x4 to a model already contains x1 and 3 is what? SSR x1, x2, x3, x4, okay, minus SSR x1, x3. Is that right? Okay. Or SSR x2, x4 given x1, x3 equal to SSR x1, x3 already in the model and adding x2, the increase of regression sum of squares, plus now x2 is added, so x1, x2, x3 given in the model and adding x4, the increase of regression sum of squares. Either way, we can calculate this kind of what? Partial sum of squares. Why we need this kind of a thing? For the partial what? Testing hypothesis, beta 2 and beta 4 equal to 0. Okay? Then but x2 and x4, both of them are unnecessary in the model. That means, so we need partial sum of squares for test this kind of a partial test hypothesis. Understand that? Okay, it is a little complicated, but sometimes necessary to know when you deal with some empirical data. Okay. Okay, this is it today. I'm going to continue the last stage next time. Thank you. Bye.